by defining a free product of groups. I promised a very simple example. So consider G be a free product of two copies of a cyclic group. So how each of them just contains two elements, one and a generator A, such that A squares to 1, and this contains also two elements, 1 and B, where B squares to 1. So again, not to confuse, there are two different copies of the same group, so we need to denote generators differently. So by definition, so as a set, is a set of words, finite words of the form. So we start with A, then it should be A, B, A dot, or it can start with B. And multiplication of words works by just concatenation of words and doing the reduction. So for example, if I want to multiply, for example, this word to itself, so I write it like this, and then I start, okay, there's two guys from the same group, so I have to do this reduction. If it's 1, I just erase this, so I get this, then I...
So the ones are removed?
Yeah, the ones are removed. If I get a 1, actually, because in the definition of the word, all letters are not 1. All elements are not equal to 1. And then I get this, and this is, well, this is an empty word, which is identity. It's an empty word, which is by definition is identity. Okay, so let me also do the following remark. So if you have a homomorphisms so we have family as a definition of the free product. We have some family of groups H alpha denoted by index alpha, and suppose for each of these, for each of the group in the family we have some homomorphism to some fixed group K. Then we can define a free product of these homomorphisms, so denoted by a star product of 5 alphas, and this will be a homomorphism from the free product to K, such that so the elements here are words like this. Each of them is not equal to 1, so there are words like this, where Gi belongs to, say, H alpha I, and this word is mapped to a product of the images and the corresponding homomorphisms. And here, of course, we take a product in K using the group structure in K. And this is indeed homomorphism, so it's easy to, by the definition of the product, here, which is concatenation of words, you immediately see that this is the concatenation of words is mapped to product here. And of course, the reduction operation is also, so you can reduce a couple of elements. We can also multiply by multiplying them in the same group. We can also multiply them here. Okay. So in this lecture, we will essentially what we're going to do. We're going to prove one Campen theorem. But before we formulate it, let me introduce the following notations. So. So we will assume conditions of the lemma that we had in the previous lecture. The reminders are x. Just to briefly remind you, the conditions was that the x was a union of open subsets A alpha, so that each of them contain x0, a fixed point here, and the other condition that they was they were all connected. By themselves, they are all path connected, and the pairwise intersections are path connected. And, so, assume we have this this covering of x by this A alphas, which satisfies the condition. Then one can so the first notation which I want to introduce is I alpha. This is the inclusion marks of the corresponding subspaces into X. And one can also consider I labeled by pair of indices alpha beta. And this will be inclusion of the intersection of the corresponding pair into A alpha. And then of course, I want to consider, so in order to simplify writing, I want to define, just denote, and use a particular notation for the corresponding push forwards. So the push forward corresponding to I alpha is known by just J alpha, and so this is a map homomorphism from pi 1 of A alpha. So since all of them they contain x0, so I can always for any fundamental groups, I can just take my base point to be x0. So homomorphism to pi 1 of x x0, and similarly, J alpha beta is the push forward of I alpha beta. This is just notations. No material statements.
Does the map you erase has a particular name?
All free you can call it free product of homomorphisms. So now we're ready to formulate one complex theorem, which will allow to calculate the fundamental group in many examples. And so again, we assume the situation as we had in lemma. Satisfied all these conditions, and then there are two parts. First part is the following. So consider phi the free product of homomorphisms G alpha. So this will be so each. By definition of this product is the map of the free product of fundamental groups of A alphas to one of X, and the statement this is this homomorphism is surjective. And the second part is the following. So moreover, if in addition to these constraints, all triples are cross connected, then we also know a kernel of this map. So we know this map is surjective, but if we have some additional constraint, we also know what is the kernel of this map. So we know this kernel by n. And the statement this kernel is so first of all, is a always the kernel is a normal subgroup. So it's a normal subgroup of this free product of fundamental groups A alphas generated by elements of a certain form. Yes. Where omega is the element. Omega is any element of pi1 of the corresponding pairwise intersection. So this gives me an element. So if I take any element omega here from this group, so this gives me element of pi1 of A alpha, and this gives me element of pi1 of A beta, and the product is of course is an element in the free product. And I can see the normal subgroup generated by this element. So this is a formulation of the theorem.
In this notation, the brackets are for the class.
No, this is just inverse. Just inverse element in this. The inverse element in pi1 A beta. And this is the element. Just inverse. So proof. So the first part we actually already proved. This is actually proved in that. So in lemma we showed that any so if I take any class of some loop here in X, I can always represent it, decompose it into product of loops, into position of loops, so just each loop lives in some A alpha. So this means I can always represent this element by product of elements. Okay, so this was easy, but the second part will be actually pretty hard and technical. It will take some time to show the second part. Okay, in order to facilitate the argument, let me introduce the following terminology. So let us call a formal product or a word like this. It's a sequence. It's a formal product, so I just consider this as some sequence of elements where each guy is an element in pi1 of A for some index alpha I. So it's represented by some loop in which is contained. So I consider this a loop in X, but whose image is completely inside this subset. Let me call it a factorization of an element which is a class of some path F in it's an element in pi1 of X. If so, I haven't finished. finish the statement. So if F is homotopic to this composition, this means path homotopy X. So this, first of all, this always, from the demo, for example, we know that such factorizations always exist for any element here. Factorizations always exist from lemma. Exist. So what you note that unlike in the definition of the free product of groups, here we don't say that the neighboring elements, we haven't specified that the neighbor elements should be from different groups. So far this was just a definition of factorization of some class in the fundamental group represented by some loop. But so we want to consider certain equivalence relation between different factorization. First, so this is kind of similar to what we had in the definition of the free product of groups. So we have if you have two neighbors in this formal product which belong actually the same group for some alpha, then we declare it to be equivalent to a factorization where we recompose the corresponding loops inside the alpha. This is also an element. And so this is the first equivalence relation. And the second. Second equivalence relation is as follows. Suppose I have somewhere in my formal product element I1 of A alpha I. And so let me, we always have, so x0 belongs to any of them, so I will omit, for simplicity, I will omit what follows, the explicitly things specifying the base point, but we always this base point for us in this proof will be x0. But suppose it happens that the image, so if I understand this loop in X, so suppose its image is actually happens to be inside of an intersection between this subspace and A alpha j for some alpha j. Then I declare this form product to be same as this factorization, same as this factorization, where here I understand this guy, because also it's denoted the same, but here I understand this element as an element of pi 1 of alpha j. Since this loop belongs to both subspaces, I can also understand it as a representative of a class here. So I can change, so this is a different, by definition, this is a different factorization, because in factorization I have to specify to which group I take an element. But I declare this pair to be equivalent.
What is im of A alpha I intersection A alpha j?
Oh, sorry. It belongs to this. Okay, so so what is another way to formulate this? Another way to formulate it is as follows. So since this loop is contained inside this intersection, I can also consider element omega, which is a class of this loop inside pi 1 of the corresponding intersection. And then this guy, by the definition of my maps J, this is a J choose a bad notation. Well, anyway, let me just stick to it. Yeah, no, sorry, I will have to change it. So let me take this just alpha and here this beta. This will be easier. Just alpha and beta. So this belongs to some A alpha and pi 1 is A alpha, and this belongs to pi 1 A beta plus some alpha and beta. So then this guy is J alpha beta of omega. And this guy is by definition of J, this is a J beta alpha of alpha. Now this I can rewrite as follows. I can write this J alpha beta omega times J beta alpha of omega inverted times J beta alpha omega. And this is, as we saw, belongs to M by definition. So N was generated by all elements of this form, where omega is some element in pi 1 of a pairwise intersection. So this means that so the second equivalence. So the first equivalence relation was just reduction of words, as we had in the definition of the free product of group. And the second equivalence relation is equivalence after multiplication by an element from this normal subgroup N in the free product of groups. So therefore, equivalent, this means that combining these two statements, we see that equivalent factorizations they give the same element. In well, let's say, do I need a, I don't know, just in this free product by one, so alpha quotient by n. So by free product, of course, free product gives, I mean, by free product I can, so by applying this reduction I can always, which was the first equivalence relation, I can assign it some element here, and then the second equivalence relation gives me that the fact, corresponds to the fact that the equivalent factorization defined as this, they produce a different class with respect to quotient over this normal circle. Okay. But we want to show more. We want to show that, so the second part was a statement that this group, the second part of the theorem was a statement that this group is isomorphic to phi1 of x. Because it was a statement that the kernel of the smart phi was exactly. So what we want to show, and this statement corresponds to the fact that any, so if you take f, if you take some element in x, and any two factorial, if you take any of its factorizations, they will actually be equivalent. So they're exactly one element, one equivalence class here for any loop in X. Okay. We want to show any two factorizations of some fixed element of x are equivalent. Or this means that this so the map, so the original map was written by phi, but we consider the map as corresponding map from the quotient to phi1 of x, and so this map works as follows. So we have a factorization, some factorization, and so the second, the exterior bracket denotes the class with respect to this quotient, and it's mapped to the class of the composition of these loops, of the small, kind of small loops inside, which live inside the subspaces. So I want to show that this is injective. I already know that this is surjective, but I want to show it's injective. So let me take two different factorizations of the same guy here and show that they are shows that they are actually equivalent. First factorization like this, and the second factorization, let's say by k 1, two different factorizations. So what does this mean? This means that well, we need to take so we are given that these two different factorizations use the same element here, but this means so we take compositions of the paths here and then composition of paths here. This gives me two paths in X which are path homotopic. There exists a path homotopy which will be denoted by F. Path homotopy in X such that it is a path homotopy from composition of these guys to composition of those guys. Any questions so far? So now we're going to use a similar trick to what we have to do some analysis to show this. So we're going to use a similar trick. So we use the fact that f is continuous and the fact that it's defined on a compact. So I'm not going to repeat the full argument, how one goes from this pair of statements like this is compact. We have two properties like this, and from them it follows there exists a finite cover of finite cover, so it's compact. So of course f is continuous, so I can take for each point I can take a neighborhood, so it maps completely to one of its images inside A alpha for some of the alpha. And then, of course, I can, like result also generates, I can assume that these neighborhoods are products of intervals, open intervals, but then I can reduce them, make them smaller by assume that these intervals are actually closed intervals. So this means that, in particular, there exists a finite cover, and then I use compactness, which means that there exists a finite cover of this square by rectangles form such that each rectangle is inside the image of each rectangle is inside a alpha for some alpha. So before we did this the same argument, the similar argument was done for intervals. We did this already a couple of times. So here it is the same, but for product. And then also similarly. So we have some so covered by some rectangles, but then similarly to what we did for interval, you can always take a certain smaller subdivision, which is by taking dividing this rectangle by horizontal vertical lines which pass with coordinates being all possible points here in this finite cover. So we end up with partitions of these two intervals. Like this, and let's say, sorry, this is going to be divided by n, and this is m, like this, such that for each f for each small rectangle taken by this subdivision is inside some, let's say, A alpha, A jet.
The index for the product isn't it J for OC?
This is J. So let me so to give you an example, so there will be first things one can, yeah, we will have to use this picture to explain stuff. So let me, it's easy to visualize some simple example. Suppose we have a line here. So this is t-axis is t1, t2, t3, t4, which is the same as 1, and we have something. This is 1, this is 2, this is 4. So we argue that there exists some subdivision like this, so that each small rectangle is mapped completely inside some particular one of the subsets. But it will be difficult to work with this subdivision. So what we actually assume, we want to first modify. So we assume is the following. We can do a small perturbation . You can always do something, which means this the edges in this mechanism, some graph So I can shift edges, the vertical edges by sufficiently small by sufficiently small distance in the horizontal direction, so that this property is not spoiled, but the new subdivision will look something like this. So I do shifts, for example, here, like each other row. By doing this kind of small shifts, which do not spoil this condition. And so what is important here is that, so you do a small perturbation such that now each vertex here in this subdivision meets, so now each vertex meets at most 3 edges. Before we had this kind of singularity, in a sense, bad situation for argument, for logical argument, that each vertex here, they need 4 edges. But now, once we do the shift, each vertex is connected only to at most 3 edges. And also, let me relabel rectangles the partition of this square by R1, R2 till Rn times n. So there was m times n rectangles here. And so now I will denote these rectangles just by ordering them in this direction, in this way. So R1, R2, R3, R4, R5, and then I go here R6, R7, till R times n. Okay. And again, so this perturbation can be always made small enough so that we don't spoil this condition. So now we denote in our new notations this f of Rr will be a its image of Ri is rectangle will be inside A alpha I. So now this index I has a different meaning to what we had before. Questions? So let gamma R be a pass this square that separates so R will be vary from 0 till mn, and this will be a pass that separates rectangles, union of rectangles R1 till R R from the rest. This means the following. Some example here. So, for example, gamma 6. So, okay, maybe gamma 7 will look something like this. It separates first 7 rectangles from the rest, and goes from this edge, from this vertical edge of this full of the square to the right edge, and so this in particular will be gamma 0, and this will be gamma n. And this whole rectangle by f, by my homotopy f, it's mapped to x, and in particular from the fact that it's a homotopy of loops, follows that this edge is mapped just to x0, and the image this edge is also here, and while the composition of gamma 0 with x gives me the first pass in the and the composition of f with this gamma gives me the second pass. So namely, what I want to say is the following. So f is a pass. Now remember that f is a pass homotopy in x. And so if I compose f with gamma r for some r, this composition is a loop in x, since its value at 0 and its value at 1 is the same as 0. So this is because gamma r starts with this edge, which is mapped to x0, and ends on this edge, which also mapped to x0. So the loop in x, starting and ending at our fixed point, base point x0, and okay. So let me also take some vertex here. Consider some vertex. Any vertex in this subdivision. And so by our construction, each vertex B is adjacent to at most 3 rectangles. Let's say R51, R52, R53 for some indices. And this guy is adjacent this guy, this guy, this guy. Okay. And we also know so also we know that well, we remember this condition. This is the image of each rectangle is inside A alpha I, and combining these two statements, we see that there exists a path. There always exists for any vertex V. There exists a path which we denote GV. It's a path inside the triple intersection of my subspaces A alpha corresponding to these three rectangles which surround this vertex, namely A alpha AI1, A alpha I2, and A alpha I3. Of course, this can be also understood as a path inside X. And it's a path from X0. So we know that this is so all this we know these triple intersections are path connected, and they connect, and they all contain my base point X0. There exists a path from X0 to the image of the vertex V under my homotopy. So the image of this case here. As we know from this statement and this statement, we know that f of v also belongs to this triple intersection. And we know that this triple intersection is path connected. So G. So for each, so you consider, so we define for each r from 0 to m times n, we define a path inside this unit rectangle, which is denoted by gamma r. So for each path gamma r, there is a corresponding factorization of this composition. This composition represents an element of pi 1 of x, as we understood. And so what is this factorization? This factorization is the following. So this thing is path homotopic. So how do we construct this vectorization? So first we can note that this is path homotopic, of course, to well, let me draw. So let me zoom in what is going on here. So we have a path. This gamma R, and well, I can get some vertices, meet some vertices, so V1, V2, V3, V4, and then dot, some vertices on the path, and what we want, you can split this path into a subpath, which will denote, let's say, let's see, gamma R1, gamma R2, and gamma R3, and so on. With a small subpaths which go along gamma R, and they connect to neighboring vertices. And so then, of course, gamma R is a composition of these small passes, and then I can use, well, if I write it, well, suppose the last one, the last small pass here is gamma R, I don't know, BN. This means that this composition is homotopic to, pass homotopic to this composition of pass. And so then we can do the similar trick as before. This is so this vertex is V, let's say V n minus 1. I can insert, what I can do, I can here insert a path which my path which goes to this point, G pass GV n minus 1, and it's inverse. Do it till then where I insert here JD1 bar F composed with gamma R1. You can do these pairs of paths, insert pairs of paths GB and the inverses. So this is consistent because this goes from this passes from x0 to this image to f of this vertex, and this path starts at this f of this vertex. Okay, and but then by construction, this is a I see that this is so each of these guys belongs, well, let's see. Each of these guys belongs to let's say it's like a beta and this one for some I. So why this is the case? Because well, we acquired. So we know that this is by construction. So we know by construction of this. So this for this guy we know this is the case. We can choose some A, but for G we know we for this G corresponding to vertex we acquired this lies in the same subset as all three subsets corresponding to this neighboring rectangles. In particular, to be more specific, so if I have like this, again, this locally picture looks like this, have some small paths like this between two neighboring vertices, let's say Vi minus 1 and Vi, and so here, let's say I have rectangle RA and here RB, so some A and B, and so this this element, this small small path here corresponds to a factor in my factorization, which is a class of the following loop. And I can treat it well, by choosing, so I can actually two choice, I can choose it A, my subset big A, either corresponding to this rectangle or this rectangle. I can treat it either as element here or element by alpha B. So this path provides me a factorization. The associated factorization so that each is a formal product of elements like this, so that each element corresponds to a small edge which lies along this path gamma. Again, this is well defined because we chose this subdivision and chose those passes G so that they lie, the images is completely inside both of these guys. Questions? So let me know the following. So, but so it seems that there is some ambiguity, so we can kind of have a different factorization depending on how we treat, like how we treat this guy, the element of this guy and this guy. But it's a catch because this ambiguity this group in the formal product, this ambiguity results in two equivalent factorizations. So as you remember, our second equivalence relation was exactly this changing these formal products by changing the group where this element belongs to. And also, second statement is the following. So factorizations corresponding to gamma r and gamma r plus 1 are also equivalent. Why z is because, so what happens if you compare passes gamma r and pass gamma r plus 1, so gamma r plus 1 it looks something like this, so I just shift it by one small rectangle. This is r here, and so it can we can see, so I can consider path homotopy between those two paths inside my inside my square, just by deforming, keeping them the same here and deforming them completely, doing deformation completely inside this small rectangle. So I can, for example, I can choose explicitly some linear homotopy as you can before. So this pair of paths are related by homotopy, by path homotopy. Let me denote it by G, path homotopy G in this means that for any value of the homotopy parameter, which we usually denote by T, it's the image. So we have some paths, the one parameter family of paths, so each of these paths in the family, its image lies inside either along those original paths or inside this small rectangle. And then it follows that the corresponding compositions of this pair of paths and my map f from this unit square to x are related by a homotopy, a path homotopy is a composition f and g, and so I can only, so if I fix this, again, I consider my factorization, and I only change, so in my factorization, I'm only caring about what I do with compositions of f with this small subpath here, and so I take a path homotopy between this between the corresponding compositions here, and by construction of the subdivision, I can assume that it's inside A alpha r plus 1, because this is the image of this. This is because the image of of this small rectangle here. So this is this is our first one. So this means, so I can consider, so if I yeah, by choosing this, so in my choice of factorization before, I can choose these guys, the components of the factorization here, both here and here, to be both in the same, in pi 1 of the same A, corresponding to the small rectangle. And then just the corresponding homotopy, the classes will be just the same if I do a homotopy like this. So this is an explanation why factorizations corresponding to this pass gamma r and gamma r plus 1 are equivalent. So of course now we want to consider like what happens at 0, one for gamma 0 and gamma times n. So it means the following. So you can assume that so S partitions. Partitions of this interval and this interval at t equals 0 and t equals 1 subdivide partitions used in the instruction. For factorizations which I need to compare. So this was first was denoted like this, and second was fk prime. So this can be just by taking this, by taking intersection of two partitions. So for this guy, so this is the factorizations. The partitions for these guys, they are the same. They tend the same way as we did in lemma last lecture. So here we can just take intersections of this of the points. Sorry, the intersection of two partitions. Okay. And so of course we consider, for example, gamma 0. So the composition of f with gamma 0, it's equal to f, and f is factorized by these guys, and So what does it mean that we have a so this one partition subdivides the other. So we had a, so this is what happens at t equals 0. We can zoom in somewhere here. And so there was a subdivision of the partition which gives me this factorization. So it goes something like this. We have fj minus 1, fj, and then fj plus 1. But then we first subdivide it like this. So this is where, in particular, our vertices in this subdivision here y. So we have something like vi minus 1, vi plus 1, dot. So the blue guys are the vertices. And somewhere here, well, of course, I have, for example, here I have Ri, here I have Ri plus 1. And here I have R plus 2 and so on. Okay, so I have a situation like this. And so we had a condition that the image, so for each vertex here, so for some generic vertex, it requires the image, so we define some path GV, and it was required to lie inside the open subsets in X corresponding to these three neighboring rectangles, but here we have only 2. So for each vertex is connected to only two small rectangles. So we have the previous condition is reduced to just this condition, that this lies inside an intersection like this, and so we actually have so we can add to this condition the following. We can also require that this guy belongs to a third guy. This is because a triple intersection is path connected. A triple guy such that this third subset also contains the image of fj here. So this fj was, by construction, it was contained in some a beta. Okay. Good. So now this means okay. So if I make these additional requirements, it follows that factorization. So indeed, factorization corresponding to gamma 0 is equivalent to this original factorization. this is 0.3 and 0.4. Similarly, so we can do the same argument for H for this gamma mm on top. Similarly, factorization corresponding to the top pass is equivalent to the factorization which we the second factorization which we want to compare. This was a factorization of paths which obtained by composing this guy with F. Okay? So what we learned, these 4 points, is that so first of all, each path, each this gamma R gives me some factorization. Second, and then also if you change this kind of jump like this, this jump provides me an equivalent factorization. This kind of, yeah, and also the factorization corresponding to the first pass here and the last pass, they correspond to these 2 factorizations, which we wanted to show. We wanted to prove the 2 original factorizations, which we wanted to show that they are equivalent. And, this means that these 2 factorizations are indeed equivalent. So this is this is what we want to show to show that the mark in the theorem, the point that is in the second part of the theorem is eigenvalues. So this hope you follow this subset. But again, the main idea is to use this, to use the homotopy, but you have to use some analysis to do the small decompositions and do stuff in small steps. So, okay, actually, well, it's almost time, but so, okay, there was some example which would be relevant for your homework, but I don't know if you want me to stop or because in principle you already know what is the one complex, but well, if you don't mind, I will take a few minutes to give you some example because it will be helpful for your homework. Actually, but I thought that would finish early. So this will be relevant for the very last question. So let me X to be a which sum of topological spaces Y alpha. So by definition, so we fix Y alpha for each topological space, and so this thing is defined by we start with the joint union, and we quotient over equivalence relation. The equivalence relation is just saying that we identify all pairwise all points are all selected points here. You just can visualize it where you have some bunch of closed space and you glue them at a single point. And so suppose that so for any alpha, y alpha has an open neighborhood u alpha which deformation attracts to this point, this selected point. Then the fundamental group of X, this base point X0, which is a class of any point here, so all those points are grouped at the same point, is the free product of these fundamental group of those spaces which appear here. So how do we see this? This is quite simple. And so in the Van Kaplan theorem, so we take in the alpha to be the following: the y alpha which with b all neighborhoods in other spaces. We can understand that so you had some x was looked something like this. So y1, so y2, y3, and so on. And for this a alpha, so for example a1, what we do, we keep y1, but from each of other guys we just keep a small neighborhood which satisfies this condition. And then so we know that this deformation attracts to y beta. This means that I can retract all these guys to a point, but this means that a alpha attracts to just y alpha. So you can retract all those guys to a point. Okay, and moreover, if I take intersection of any pair, so this would be just for alpha non-equal to beta, this will be just bridge sum of these neighborhoods, and this retracts to a point. Just retract. I can all of them retract to a point. And so this means in particular pi1. This intersection is 1 for alpha, and in particular, the normal subgroup was given by some images of elements here. So the normal subgroup in the Van Kaplan theorem would be trivial, and this means that pi1 of x we don't have to divide by anything, so pi 1 of x will be just a star product, well, the free product of pi 1s of a alphas, which is, we show that this is, because this is deformation attached to y alpha, this will be free product. So anyway, yeah, so what we learn is